my name is Graham Junsar, and this is my video lab report on Lab5, magnetic braking with Faraday. The purpose of this lab is to compare the experimental time it takes for a bar magnet to fall through a conductive tube versus a computational model created using Faraday's law. The models and fundamental physical principles used in this lab are Faraday's law, magnetic fields, magnetic forces, and Ohm's law. From our experiment, we calculated the travel time down the tube to be 1.338 seconds, and our computational model predicted it to be 0.618 seconds. The equation in the bottom is Faraday's law, which states that a change in magnetic flux through some surface creates an induced EMF on the boundary of that surface. In the top right is the formula for the magnetic field of a magnetic dipole, and bar magnets are magnetic dipoles, so that's why we're using that in this lab. In this experiment, our system is the bar magnet, and the surroundings is our aluminum tube, along with a constant gravitational force downward supplied by the Earth. The initial conditions of this experiment are a bar magnet positioned at the top of the vertical tube with zero velocity. For our experiment, you need a bar magnet, an aluminum tube, a meter stick, and a stopwatch. First, you need to find the length, diameter, and thickness of the aluminum tube. Then we need to find the mass and magnetic moment of the bar magnet. And we need to actually perform the experiment, we have to drop the magnet down the tube 5 times and average the travel times. So what we got from these measurements is that the average travel time was 1.338 seconds down a 0.465 meter aluminum tube with an inner diameter of 0.0356 meters and a thickness of 0.0035 meters. The magnet's mass was 0.024 kilograms, and the magnetic moment was 3.1172 amp-meters squared, which we calculated in Lab 3. The magnet falls much slower than it would for free space is what we observed. Here is some of the code in our computational simulation. In the top, you can see where we input our known values, like the length, width, and mass of the magnet and its magnetic moment, and so on. And then right here, using the equation for the magnetic field of a magnetic dipole, we're simply taking this equation and putting it into code. And in this function is to calculate the change in flux over time for a specific ring in the tube. And we use this formula, which was provided to us in the video lecture 43, and we're simply translating that into code. So to continue, we use our deflux dt calculated here, and we also want to find the force of the magnetic dipole against a particular ring in our tube, and we're using this formula where the change in force is equal to I times a little bit of length cross B, and we actually use this for the whole ring to get the whole force. So we have to integrate around the whole ring, and that's where this L would have to be along the circumference of the ring, so that's where this 2 pi r comes in, and so on. So we can translate this into code, and then to find the net force, we simply add the gravitational and the magnetic force. And finally, we just update the velocity of the bar and its position with standard kinematics. And so in our model, this shows the velocity of the magnet with respect to time, and you can see it sort of drops off towards the constant and then increases as it exits the tube. And with our simulation, we calculated it to be 0.618 seconds. Now, this is pretty far from our experimental, so what are some sources of error that could cause that? So in the actual experiment, one of our lab members was holding the tube for the experiment, and because we're using Faraday's law, which involves an induced current in the tube, perhaps by touching the tube, we interfered with the current in some way. And something that also would slow down the magnet, which we're not accounting for in our model, which would lead to this increased time, is that the magnet most likely hit the sides of the tube while it was falling, causing friction and causing it to spin, slowing it down. If the resistivity of the conductor was reduced as close as possible to 0, the magnet would fall much slower as the current would increase drastically, so the opposing force to the movement of the magnet would increase drastically. And if holes or slots were cut into the tube, then the ring currents in the model would not be able to form a complete circuit. So it would have to be a magnetic dipole pointing in a direction not directly against the magnet, so it would not be able to slow it down as much.